Bless you. All right. All right. So we are going to get started talking a little bit more about the pH scale and the calculations that kind of go along with it. So to start off with, if you see a number in brackets like that, that's telling you that it's the concentration of whatever you're looking at in molarity. So in other words, oops, I did not mean to do that. If I had 0.33 molar, would be the same as 0.33. Just another way of expressing it. We kind of tend to use it a little bit in this unit. Remember again that if we are dealing with acid, we're interested in the H plus concentration, or we might see it as H3O plus. And from that, I can get the pH directly. If we have a base, we're going to end up with information about our hydroxide concentration. And from that, I can get the POH. pH is what we deal with more. Usually questions ask for the pH, but if you're working with the base, you're going to have to get POH first and then go to pH. So those take a little bit of extra step, but it's a really easy step. All right, so the pH scale indicates the hydrogen ion, which is your H plus concentration, or hydronium, in a solution. So it's looking at how many of those ions are in solution. The more ions that are in solution, the more basic it is, and the lower the pH would be. And the pH scale is a logarithmic scale, which if you look at it as my concentration, because that's what we're measuring with all these numbers, as my concentration gets lower, my pH actually gets higher. Right here where we have our -7, that's where the pH would be equal to 7. And then down here, we're going to go to 14. So even though we have a very small concentration, my pH number gets larger, and it's opposite on this end. For that, it shows it going down to 1, where we'll actually might see some things that are below 1. So the POH scale indicates the hydroxide concentration in the solution. So same thing. The more hydroxide ions I have, the more basic it is, my pH number would go up and my POH number would go down lower. So if you have pH and POH, they add up together to equal 14. We'll use that quite a bit. And that's 14.0000. That does not affect my sig figs. So my sig figs are going to come from places behind the decimal, from either my pH or my POH. All right, so if something is acidic, we say it can go from 0 to 6.999, just right before I get to 7. Neutral would give me a 7, and then on the other side of that, right after I pass 7, on up to 14, those are going to be my basic solutions. So if we look at some common household items, which is what we'll do next week on our lab, probably on Tuesday, we can kind of see what the pH of them are. So citric acid from a lemon juice, its pH is 2. If I wanted to find its POH, I'm just going to do 14 minus 2. So that would give me 12.0. Make sure you always look at the pH to decide whether it's an acid or base. If you look at the POH, it'll end up flipping it around for you. So since my pH was 2, that's an acid. Pure water, 7. So 14 minus 7 gives me 7 also. So that one would be neutral. And then my last one, milk of magnesia, which is like used to neutralize stomach acid. its pH is 10, so its POH would be 4. And that is a basic substance. Notice that all of these I gave a place behind the decimal because I was working with numbers that had one place behind the decimal. Yesterday we learned that water is amphoteric, which means it can act as an acid or as a base. And because of that, when you have a cup of water, a glass of water, pool of water, whatever you have, it will go through a process called auto-ionization. So auto means like kind of spontaneous. You don't have to put any energy in it. And ions are going to be our charged particles. So what is happening, I have some water molecules. One of them is acting an acid. One of them is acting as a base. And I end up getting some of my hydronium and hydroxide ions. These all three are in water. So the water we drink has some hydronium and hydroxide ions. The reason it's not acidic is because they're usually very low and they're equal to each other. The ion product constant for water is represented with a KW. We don't do this, or we don't use it that much. In Chem 1, use it a lot in AP chemistry. And KW is always equal to the hydronium concentration times the hydroxide concentration. When the temperature is 25 degrees, which is considered a standard temperature. Remember, STP was about gases. This is considered like a lab setting. Then that value of KW is going to be equal to 1 times 10 to the negative 14. So a water solution always contains your hydroxide times your hydronium is going to give you 1 times 10 to the negative 14. KW does vary with temperature, so that's why it keeps repeating that it's at 25 degrees. If we change the temperature, it's going to change the KW, and it would change that relationship a little bit. All right, that last is kind of what we did yesterday with our journal. We're just looking at concentrations and how they're related to each other. So on my first one, my hydrogen ion is related to my acid and my hydroxide is related to my base. So when they're equal to each other, they would be neutral. So I'd have a pH about 7. On the other hand, if I have my hydrogen ion greater than my hydroxide, then it's going to be acidic and my pH would be less than 7. And then I have my other situation. I have my acid component is less than my base component. So now I'm going to have a pH greater than 7. All right, so we have some formulas that we use during this unit. Like I said, they're very calculator based. And this is all of them right here at the top. So on these two, if I need to find pH or POH, I'm going to use those. And that would mean I have to have, don't need to write all that, have the concentration. So in other words, if I need pH and I have my concentration of my hydronium ion, I just need to do negative log in my calculator, and that will give me my pH. On these two, I would need my concentration. So that means I don't have that. I have my pH or my POH, depending on which one I'm talking about. And I would just take 10 and raise it up to the negative one that's appropriate. And that would give me my concentration. So if those 4 things, if you have one of them, then you can relate all the rest to each other. Also, this one, like I said, comes in handy a lot of times. All right, so let's just start here. We'll look at sodium hydroxide. So sodium hydroxide is a strong base. You have to recognize it as a strong base. And so we said if a strong base is in water, it's going to ionize 100% to its ion. So in this case, it's sodium and hydroxide, and it's on a 1:1:1 mole ratio. Everything is just 1 moles. So if this is 0.001 molar, because they ionize 100%, so are these. We've done that now in a couple of different units. So since we're talking about pH, that's what I'm wanting, then this is what I'm interested in. It is a base, so I can't go straight to pH. I'm going to have to go through POH. So I need my POH, which would be right here. So I'm going to say my POH is going to be, and I'm using my formula here, negative log of my concentration, 0.0001, just one little sig fig. So if you put that in your calculator, if you want to give it a try, I think it gives you the first parentheses and then you have to close the second one. Lost myself. All right, so what did we get on that one? 3. Now, and pH and POH don't have a unit. So, you know, you'd have to say something like 3 is equal to the POH or something like that. I'm going to tell you why I put a 0. Oh, that's what you're asking. Sig figs are a little tricky for pH and POH. Once again, I didn't make the rules. So for significant figures in pH and POH, you want your numbers that are behind the decimal are the only ones that count as being significant. So in other words, this was 1 sig fig, just like we've always been doing. So when I got my answer, I needed to have one place behind the decimal. So it would have 1 sig fig too also. So here's another example. If my pH is 12.01, I need to recognize that that's 2 sig figs. So then if I need to use it, one of my formulas to get my concentration has to be in 2 sig figs by our kind of original rule. And I'll kind of talk about that more as we do some other examples. All right, a little bit about acid rain before we flip the page. So many industries produce a lot of gases that are pollutants, and these compounds are in the atmosphere and then they mix with water, whether it's rain or whether it's just with the moisture, the humidity. And then as they fall to the ground, they become what we call acid rain. If you think about it, if I have some NO2 gas and it finds some water, it's going to form nitrous acid. So that's why if you've ever heard it called acid rain, that's where it's coming from. A lot of our newer buildings that doesn't really affect, but sometimes some older ones or some statues that are kind of made out of marble or like that lime that looks a little bit like concrete, it can affect those and kind of make them wear a lot over the years. All right, let's look at some examples, I think on the next page. All right, I am just gonna jot down my formulas. Oh, thank you, ma'am. That we might need, so we're gonna keep flipping back and forth. All right, if I need, oops, first of all, we'll turn that on. pH is gonna be negative log of my H plus concentration, POH, negative log of my hydroxide. So that's if I need one of those. Now, if I need my concentration, then it's 10 raised up to the negative pH, or my hydroxide, 10 raised up to the negative POH, the So that's if I need one of those two. And then 14 is equal to pH plus POH, always comes in nice and handy. All right, so then we don't have to flip back and forth. So my first one, what is the pH of a 3.4 times 10 to the negative fifth molar hydrochloric acid solution? Oh, actually, I'm going to change that. Let's change that to sulfuric acid, H2SO4, which is sulfuric acid. You can keep your strength. I mean, yeah, the molarity can be the same. So my first thing that I need to do, I need to recognize that as a strong acid. So it's going to ionize in water. Sulfate, I'm not really worried about my sulfate. I'm worried about this hydrogen ion. And because it has a subscript of 2, there's going to be 2 of those. So what that changes is if this is 3.4 times 10 to the negative fifth molar to begin with, on this side, it's going to be 2 times that. Because I have 2 ions for every 1 ion of my original acid. So if you forget that, then that messes you up a little bit, or actually would mess you up quite a bit. So when I do that, what did I get? Messy work. So I did this, I got 6.8 times 10 to the negative fifth molar, and that is my H plus concentration. So I want my POH, so this is now the formula I need to use. This is 2 sig figs, so when I get my answer, there should be 2 places behind the decimal for my pH. So I'm going to circle, I'm going to say my pH is going to be equal to the negative log of this, 6.8 times 10 to the negative fifth. And that's what would go into my calculator if you want to give it a try. All right, what did we end up getting our pH at? 4 point what? Oh, I'm looking at my wrong one. I'm sorry, y'all. 4 point, but it's tricky because we need 2 places behind the decimal. Because remember, this is not considered significant. And once again, it's because it's on that logarithmic scale. So these are my 2 sig figs that match up to my 2 original sig figs that were molarity. And then I would need to put something like equals pH. Circle it and make sure everybody knew that I knew what I was doing. All right, number 2, nice, easy one. I have the pH of a solution. What is the pH of a solution if the POH is equal to 5? So what am I going to do on that one? 14 minus 5, right? That's going to give me 9, which is going to be my pH. No places behind the decimal because my original one didn't have any places behind the decimal. Be nice if they could all be that easy. All right, the next one kind of brings into some things that we've been using all year long. So we're looking at the pH of a potassium hydroxide solution. So this is a strong base. And when it ionizes, I just get 1 mole of hydroxide. So that means if I had the molarity of what this was, I could have the molarity of my hydroxide, but I don't have the molarity. Remember, molarity is moles per liter. But of course, I don't have the moles, I have the grams, so I'll have to do that little gram to mole conversion. So 5.611 grams of KOH. And then its molar mass is 56.11 grams per 1 mole. So in that 5.611 grams, I have 0.1 moles, and I'm going to stick some zeros behind it just for sig figs. This is 4 sig figs, so I need 4 sig figs at this point. All right, now I'm going to divide that because I got this part. I need to divide it by liters. So now I divide it by my 10 liters, which only has 1 sig fig. So when I get my answer right here, I just want it to have 1 sig fig. .01 should be what you get there. And remember, that's KOH. All right, so now I got that. So can I get my pH first? Can I go straight to pH? Do I have an acid there? What is KOH? It's a base, so I have to go POH first. So that's why a base takes one extra little step. So I'm going to do negative log of my concentration. And that's going to give me my POH. Which at this point I would get 2 with a 0 behind it because that 0 is significant. That's my 1 sig fig. And then to get my pH, I would do 14 minus 2 and I would get 12.0. That would finally be my pH. So if you're dealing with a base and you're trying to find the pH, it's just going to take that little extra step of subtracting it from 14. All right, any questions on that particular one? All right, let's look at the practice, the one that has all these lines on it. It looks a little bit overwhelming, but it's not. I can find mine. I'll put that little sucker out. Too much stuff going on. All right, so this looks pretty overwhelming, but it's not. All of those are connected. So if I have one, I can get all of them. So once again, I'm just going to jot down my formulas so y'all can see what I'm referring to, whatever y'all want to do. So I'm going to do my pH is equal to negative log of my H plus. And POH is equal to negative log of my hydroxide. So that's if I need pH or POH, I'm going to use that one. And now I'm going to do my H plus concentration is equal to 10 raised up to my negative pH. It's supposed to be an H. And my hydroxide would be 10 raised up to a negative POH. And then, of course, pH plus POH equals 14. All right, I think that should get everything that we need. So on my first one, I have the pH. So I'm going to do the easiest thing, and I'm going to decide whether it's an acid or a base. So since it's 3.78, it would be an acid. Be sure you always look at your pH, not your POH, because POH will flip it. My second easiest thing to me would be to get my POH, because I'm just going to take 14 minus 3.78. Want 2 places behind my decimal. 10.22. All right. So now I need my concentration. So I'm going to use these 2 formulas. So for my H3O plus, I'm going to do 10 raised up to my negative 3.78. Now this pH has 2 sig figs because it's 2 places behind the decimal. When I get this answer, a molarity, it should also have 2 sig figs. You're going to get a lot of really small numbers in this unit, so be sure you don't accidentally miss your exponent. All right, what did we end up getting for that? 1, we just need, that is 2 sig figs right there. And I know it's back and forth. This, when we're doing molarity, that's how we've always been doing them. The pH and the POH are changing. That's where we're just looking at places behind the decimal. So just 1.7 times 10 to the negative 4th molar. And then I'm going to do the same thing over here, but I need my P. What do I need? I need my hydroxide concentration. So I'm going to do 10 raised up to my negative POH, which was 10.22. And same thing, that looks like 4 sig figs, but because it's a POH, it's just 2, just the 2 behind the decimal. So you should get 6.0 times 10 to the negative 11. And once again, that's molarity. Are we good on that? And then if you would like the next one, now I don't have pH, POH, I have my H3O concentration. So I'm going to use that formula that says pH is equal to the negative log of that concentration. So let's see, this has 3 sig figs because this is a molarity. So when I get my answer, I want my pH to have 3 places behind the decimal. Alina, sit up. So I'm going to use this formula, negative log of that. Noah, what'd you get for that one? Perfect. Me too. All right. So once you get that, I would do a couple of easy things that look like a 3. I'd say come over here and I would say it's an acid. I would subtract it from 14 to get my POH. And then that I would use finally to get my hydroxide. So I would have to say 10 to the negative 10.590, and that should give me my concentration. I don't know why I don't remember using that number. And 3 sig figs, like our other molarity measurement. So it would be 2.57 times 10 to the negative 11 molar. All righty. So y'all got maybe about 15 minutes to do some practice. See if you have any questions for me, or if you had questions over conjugates that you are dying to know before the quiz. That also works for me.